Yihong will talk about better together, unifying data log and equality saturation.
All right, thanks. So I'm Yihong, and today I will be talking about our original work on egglog, which is a system that unifies dialog and equality saturation. So the problem we studied in this work is that people do equational program reasoning with equality saturation because it's fast. But current EqSat frameworks has only a limited support for semantic analysis, which cause real-world headaches. On the other hand, people do rich and composable program analysis in Datalog, but equational reasoning in Dialog is asymptotically slow. A natural question arises: can we build one system that subsumes both equality saturation and Datalog? The answer is yes, and we will show in this talk that in order to unify Datalog and EqSat, all you need are these functional dependencies and functional dependency repair. So in the rest of the talk, I will explain what this means. So let's first review some background. Equality saturation, which is the idea of doing term writing with e-graphs, has been very successful recently. It has been used in many domains, from big data systems to hardwares, from program annotation to program synthesis. It is also getting adopted in industry projects. It is used in chip design, in database optimization, smart contracts, and web assembly. So at the core of equality saturation is a data structure called e-graphs. This example e-graphs represents A times 2 over 2. And if we zoom in a little bit, we will see these dotted boxes as e-classes and the solid boxes as e-nodes. And each e-class contains a set of e-nodes, and each e-node has 0 or more e-classes as children. So this e-class contains a single e-node, which is A, and A has 0 children. But other e-nodes, such as the times and division operator there, they have 2 children e-classes. So we apply rewrite rules to this e-graph, and we grow the e-graph. And now, after the rewrite, the e-class in the middle has 2 e-nodes, and it represents 2 terms, A times 2 and A left shift by 1. The e-class at the top represents A times 2 over 2 and A left shift 1 over 2. So we apply for more iterations and until we reach some fixed point or timeout. One thing to note here, though, is that the rule x over x to 1 is actually not summed. For this rule to apply, x must not be 0. In other words, we need semantic information about x from this e-graph. But how can we do this? Well, existing EqSat frameworks like egg use the so-called e-class analyses to support semantic analysis over e-graphs. It annotates each e-class with an abstract value. For example, we can attach to each e-class an interval information, which denotes the possible ranges of the expressions. And when analyses are changed, such changes are propagated up to analysis of their parent e-classes. So this idea of e-class analysis has been used in many projects, but it turns out that e-class analysis has some limitations. For example, in e-class analysis, you only allow one kind of analysis. Although it's possible to define a product analysis that combines individual analyses, this will make the implementation clunky. Moreover, e-class analysis only propagate from children to parents, and this forbids certain kinds of analysis like type checking to be used, which pass context from parent to children. And finally, in frameworks like egg, analysis have to be implemented in an external imperative language as a monolithic function, which is neither composable nor scalable. But our insight is that analyses are rules too. So people have been expressing analysis in a declarative rule-based language called Datalog. And in Datalog, analyses are expressed as logical rules. And because they are expressed as rules, they are very flexible. For example, Datalog supports the definition of multiple analyses. Their definitions are modular as a set of individual rules. And these rules also compose and cooperate with each other to collectively derive more precise analyses. So here's an example rule. This rule says that if E is an expression of the form x plus y, then the lower bound of E should be the lower bound of x plus the lower bound of y. As you can see, this is very straightforward. So the question here is, can we express EqSat in Datalog to enjoy the rich and composable analysis in Datalog? And to do this, we need to express both the triggers, which are these left-hand sides, and actions, which are these right-hand sides, in Datalog. So our previous work on relational imaging shows the first half of the story. So imaging is a problem of doing pattern matching over the E-graph. In that work, we show that they are just database queries. And this actually gives us significant speed-ups. And it handles the trigger part of the story. And now, what about these actions? Well, this leads to our work on egglog, which unifies dialog and equality saturation. So one of the key concepts in egglog is functions. In egglog, every table represents a function, and a relation is just a function to the unit type. With functions, we can talk about terms and equivalencies between these terms. And here's an example term writing program in egglog. So we can define these data types with constructors in egglog, and each constructor corresponds to a table that represents a function to the math data type. And elements of the math data type will be generated on demand. We can also define expressions of the math data type. Expressions are recursively inserted into the database. Along the way, we introduce new elements of math data type to denote the mapped value of each sub-expressions. Finally, we can define right rows over these terms. The first two rows here defines the commutativity and distributivity, and the last two rows define a constant folding over the addition and the multiplication operator. So here we zoom in a little bit to see how individual rows behave. So this is the distributivity. It will match the left-hand side with relational imaging over that database. And for each match part, we track the corresponding value for each variable in the left-hand side, and we build the corresponding substitution. Then we apply this substitution to the right-hand side and insert the right-hand side from the bottom up. So egglog will insert the two sub-expressions for multiplication, introduce new elements for the math data type along the way, and then it will insert the top E node for the top level addition. Now, note that the left-hand side maps to the element C sub 5, and the right-hand side maps to the element C sub 8. And because the rewrites are equational, we also need to make sure that the left-hand side and the right-hand side map to the same value. Well, to do this, egglog uses a unified, and here we merge C sub 5 and C sub 8 in the underlying unified data structure. So now the left-hand side and the right-hand side are equivalent, and we are happy now. So at the core of egglog's functional abstraction is functional dependency and functional dependency repair. So functional dependency basically says that the arguments of a function uniquely determine the output. And this is exactly what makes a function. But what if functional dependencies are violated? Well, here's an example. Suppose we call the union operator over C sub 1 and C sub 2 here. And the union find will merge the two elements and canonicalize C sub 2 into C sub 1. Now the table have two entries, and they both have the same input arguments, C1 and C3. And this is a functional dependency violation because the same input arguments, C1 and C3, are mapped to two different values. In this case, we have to merge the conflicting elements, C4 and C5, together so that now they refer to the same thing. And this resolves the functional dependency violation. So it turns out this idea of functional dependency repair is very powerful. The same mechanism also allows us to express composable program analyses. Remember, we mentioned earlier that E-class analyses annotate each E-class with an abstract value. In egglog, we use a function from expressions to the abstract value to denote such an analysis. Moreover, we annotate each function with a merged expression, which tells egglog what to do when functional dependency is violated. So now suppose I have this table that tracks the upper bound of an E-class, and we merge C1 and C2 together. Now C2 is canonicalized into C1. And we have a functional dependency violation because the same C1 is mapped to both 2 and 3. And the merge expression tells egglog how to resolve this violation. In this case, we just call min on the conflicting value. And this gives us a new upper bound of the expression C1 and resolve the functional dependency violation. So now we have seen the core mechanism of egglog. We evaluate egglog with 3 experiments. So first, we compare with state-of-the-art equalization frameworks. And because egglog's database likes architecture, we're able to use relational imaging for free, as well as efficient query evaluation algorithms from the database community. Moreover, egglog is the first system that supports incremental equality iteration. So incremental EqSat is known to be very hard, but we use a standard semi-naive evaluation from the dialog world to make equality iteration incremental, basically for free. And the plot here shows the macro benchmarks we did. So the green line here shows the performance of egg, which is a state-of-the-art EqSat framework. And the non-incremental version of egglog achieves 3 times 34 times speed up, thanks to egglog's database-like architecture. And with incrementalization, we achieve additional speed up, and in total, we achieve 9.27 times speed up over egg. So our second case study is actually about Herbie. So Herbie is a tool that optimizes the accuracy of floating point expressions. It transforms expressions into mathematically equivalent forms, but which has less floating point errors. It works as follows. Herbie uses a set of mathematical identities to transform the input into equivalent forms. And equality iteration will populate a big set of expressions. Then it samples this E-graph and extracts the expression that is the most accurate. However, unfortunately, not all identities can be expressed as syntactic rules, and therefore Herbie's rule set is unsound. As a result, when unsoundness is detected, Herbie has to discard the result and roll back, and this makes Herbie's design substantially more complicated. We make Herbie's rule sound with program analysis over the E-graph implemented in egglog. In particular, we define the interval analysis and the definability analysis. And this makes Herbie sound in our reimplementation. So we benchmarked our reimplementation in terms of accuracy and performance. And the results show that our reimplementation in egglog achieves a comparable accuracy and performance. But we do not suffer from the soundness issue in the original Herbie. And moreover, because now we don't need to worry about working around this unsoundness, we made Herbie's design drastically simpler. Finally, our last case study is actually on the dialog side. So people have been using dialog for many program reasoning tasks, such as point analysis, type checking, type inference. However, many advanced program reasoning tasks also require equivalence reasoning, such as the sting-scarred point analysis and the Hindley-Milner type inference. And these analyses are hard to express efficiently in Datalog, because dialog does not have this fast equational reasoning as in equality iteration. On the other hand, such equivalence reasoning is supported in egglog as a built-in mechanism. So we benchmarked egglog and dialog on the sting-scarred analysis, and the results show that we achieve almost 5 times speed up over the fastest sound baseline. And this supports our claim that by supporting EqSat, we also make egglog a better dialog language. So to summarize, egglog unifies dialog and equality iteration and goes beyond. By unifying them, we get fast equational reasoning a la EqSat, rich composable analysis a la Datalog, and a fast and incremental evaluation with techniques from the database community. Finally, as something not mentioned in the talk, egglog is a standalone user-friendly language, and indeed we have a web demo where you can write your own egglog programs. So you don't need to write your EqSat applications in an external language like Rust. And this is all because of our language-based design. And that's it. Thank you for your time. And I also want to thank my collaborators.
Thank you. Any questions? You can stand up at the mic and speak.
Hi, I'm Jacob from KAIS. I had a question on the functional dependency repair. So what you said that when you detect a conflict, we merge the conflicting values, and you also said that to do this, we call a specific merge function. What I want is that is this merge function always determined, or is there like a user choice for it? And if there's a user choice, is there like always a canonical form, or does the user have to like think hard to think of a correct merge function?
Right. So So in egglog, there are two kinds of values. There are these sort value, and there are these lattice value. And the sort value are these data types, constructors, terms. And for them, the merge function is always a union. And for these lattice values, the merge function is actually the join operator of some lattice. And this join operator is defined according to your analysis. So for example, if you are checking the upper bound, then your join operator is a mean, and you can think of other lattices and their corresponding join operator.
Okay, thank you.
Hi, it's Sam from Imperial here. So one of the big problems we have in eGraphs is the actual extraction problem and kind of doing the sub-expression, common elimination, things like that. So does the combination of Datalog, can we maintain anything that helps us at that end of the spectrum as well?
So I think the extraction problem is still quite open because like people have proposed different techniques, and in fact in the eGraphs workshop, like there are many techniques for that. And I'm actually not sure if egglog can help. And actually, on the egglog side, it's actually slightly making the problem harder because in egglog we are working with databases, tuples, functions, and they are not terms. But you can still extract a term in egglog. So in egglog, we do support this term extraction, but you do have some slightly more implementation overhead.
Any other questions? Okay, so then actually since we started quite too late, so maybe we can stop here. Okay, thanks to the speaker. And the next speaker, can you come? Oh, okay. So let's see. Junyoung, can you?